the discussion session at the end. Okay, so next up we have Silvia Protopapa talking about the South Pole observations of the moon from deep impact, a synoptic perspective of the lunar hydration.
Thank you.
Thanks.
Okay, so first of all, let me thank my collaborators, Jessica Sunshine, Tony Farnham, Laurie Figge, and Michael Hearn, who recently passed away and without whom this work would be inexistent. So on 4th of November 2010, the Dixie mission successfully encountered Comet R32. This was done using the Deep Impact flyby spacecraft employing two multispectral imagers and an infrared spectrometer covering the wavelength range 1.04, 4.83 micron. During the cruise phase, several calibration observations were performed, including observations of the moon. And the analysis of the Deep Impact HRI-IR lunar data turned out to be fundamental not only for calibration purposes, but also because they helped unequivocally to confirm the lunar hydration, the lunar surface hydration, and understanding that this is a wide surface phenomenon. Furthermore, the understanding that this is a temperature-dependent process was only thanks to the DI lunar data. However, because of the low signal-to-noise ratio, it was not possible to unambiguously detect water. Understanding the importance of the lunar data and wanting to deconvolve water from OH, the Dixie team acquired more than 6,500 spectral observations of calibration stars, and several improvements in order to improve the absolute calibration of the DI lunar data. And in fact, post the Sunshine et al. 2009 investigation, several improvements in the calibration have been achieved. These involve mainly the pixel-by-pixel nonlinearity correction, which affects mainly the accuracy in removing the dark subtraction. A scatter light problem along wavelengths where the transmission is very low has been identified and taken care of. Furthermore, a factor of 2 in error in the radiometric calibration curve has been identified. All these factors together change not only the absolute flux, but also the shape of the spectral energy distribution and absorption bands. So I'm going to focus in this talk on the quartz measurements, which were obtained by rapidly scanning the slit across the northern and southern hemisphere of the moon, such that every pixel along the slit crosses the lunar disk along the same course. This figure shows the position of the quartz measurements plotted over a 750 nanometer Clementine base map. We have two northern hemispheres quartz measurements acquired on June 2nd, 2009 on the evening and morning sides, two mid-latitude and one South Pole quartz measurements acquired on 12 December 2009 and two additional quartz, one on the morning side, one on the afternoon, obtained on December 5th, 2009. And the observation of the South Pole are post the Sunshine et al. 2009 investigation. Now, I want to stress that when I'm referring to a chord measurement, I'm not just referring to one single spectrum. We have, for each chord, several scans acquired at different scan rates, which are combined in order to enhance the signal to noise. Furthermore, for each scan, we have 512 spectra of the moon, which are combined, again, to enhance the signal to noise ratio. Here, the reflectance measurement of the northern hemisphere chord acquired on the morning side is shown. The radiance is converted into reflectance, normalizing by the solar flux, accounting for the cosine of the incident angle and the distance target sun in AU, covering the wavelength range between 1.2 to 4.5 micron. So we see that the reflectance spectrum shows, in addition to the 3 micron absorption band due to OH or water-bearing materials, a continuum that is composed of the scattered light, a short wavelength, and the thermal component along wavelengths due to the temperature of the surface. The DI-HRI IR data are unique set of measurements because they cover a wide wavelength range. They covers the full width of the 3 micron band and the thermal component. This is fundamental in order to understand the correlations between hydration content and instantaneous surface temperature. Notice that the M-cube and BINS data cover instead the wavelength range up to 3 and 3.4 micron, respectively. The scattered and thermal contribution around the 3 micron band, they are almost equal. So it is fundamental to have access to the long wavelength data if we want to disentangle these two contributions. Here, the comparison between the observations in white and the modeling of the continuum in red. The continuum is modeled as a sum of a scattered and thermal component. The scattered component is represented by a linear trend, while the thermal component is a black body function. The free parameters are the temperature of the surface and the slope of the scattered component. And as you can see, the modeling well reproduces the continuum. Furthermore, we derive temperatures that are consistent with time of day and span a range between 340 Kelvin and 370 Kelvin. Here, the comparison between our reflectance measurements removed of the thermal component across the full wavelength range. And in dashed line, you see the scattered component of the modeling overplotted just for consistency. Here, for comparison, the same quartz measurements, these are the Northern Hemisphere quartz measurements published by Sunshine et al. Again, as I was referring at the beginning of the talk, you see an improvement and a change in the shape of the reflectance measurements, especially at long wavelengths, and an improved enhanced signal-to-noise ratio. This is thanks to the dedicated work in terms of calibration. Here, for comparison, the South Pole quartz measurements, just to have a full portrait of our quartz. Now, let's focus in the 3 micron band. And here, what you are seeing are continuum removed spectra of the lunar quartz as compared to laboratory data of one lunar soil here in yellow. Now, in the moment in which we scale the lunar soil laboratory measurements to match the depth of one of our quartz, and we offset the data, we see a perfect match between our band shape of the 3 micron quartz measurements and laboratory measurements of the lunar soil. These lunar soil present this 3 micron band, which has been attributed to OH and or water adsorbed on soil grains. Across the full data sets, we observe two minimum, one minimum at 2.81 micron, which is interpreted as hydroxyl, and one minimum at 2.95 micron, which can be due to water or OH, depending on the bonding cation or body energies. If we focus on the band depths and variation of band depths across the full data set, here we have band depths versus temperature, and different symbols are obtained for different quartz measurements of the same day. So you see that we have a correlation between band depth and instantaneous surface temperature, with a more absorption at lower temperature, as expected. However, there is not a one-to-one correlation because, for example, if you focus on this red dot, that is a South Pole measurement obtained on 12 December 2009, you see that even though it is at higher temperature, it presents a larger band depth. Now, motivated by dehydration laboratory measurements, we looked not only at band depth, but we looked also at band shape variations across our data set. And we did this by looking at the variations in the slope of the shoulder of the 3 micron band. So you see here we have fitted the slope of the shoulder of the 3 micron band. And here we have plotted the slope of this shoulder as a function of temperature, or the 3 micron slope as a function of band depth. As you can see, in both plots, we have two main groups. One corresponds to the Maria-dominated quartz, while the other one corresponds to the islands dominated measurements. If we take two representative measurements, one for the measurements that have a higher slope, and one for the measurements that present a lower slope, and we again scale the top spectrum to match the band depth of the lower spectrum, and we scale it, we offset to see the comparison between the two. We see that there are no changes whatsoever in the band shape across our quartz measurements. Now, this seems indicating that our quartz are mainly suggesting variations in terms of composition and not variations in terms of temperature. To look for variation in terms of temperature, instantaneous temperatures, we plan on looking at spatially resolved scans of the moon, which were taken 7 days apart. This will allow us to investigate variations of hydration contact with respect to local time. In fact, we can monitor the same location on the moon at different conditions of insolation. So to conclude, we have the Dixie team has performed a huge effort in improving the calibration of the DI lunar data. They all present a 3 micron band absorption, and we have tried to correlate the shape and band depth of these 3 micron as a function of instantaneous surface temperature. The spectra show a 3 micron absorption, characteristic of OH and or water-bearing materials. No variation in the spectral shape of the 3 micron absorption band is observed, but only differences in band depth. This is suggestive of only one component being responsible for the hydration band. And future work will include the analysis, a pixel-by-pixel analysis of the spatially resolved scans. Thank you.
Okay, any questions for our speaker? Yeah, I think you were first.
I'm sorry I came in late, but I think in this last part, did I understand correctly that the difference in the band depth you said is due to hydration content? Is that the same as more? Is there just more of the OH there? Is that
yes, this is what we think. So if we go back to, can I go back? Yeah. So there are two contributions here. One contribution could be more or less OH, but also variations in the spectral shape. So what we see is that the spectral shape is consistent, but we are sensitive to Maria-dominated quartz measurements having less water content than highlands.
Okay, Rosemary?
Do you have an explanation for why there's a difference between Maria and highlands?
I know that several, so that also in literature this has been found, so this is consistent with other works. I will look into it as a next step.
Okay, then we've got time for another one, yeah.
So from this slide, you can see the shape has some variation, but in your conclusion, you said that there is no variation in the shape.
Correct. When I saw it, I had the same feeling of saying there are changes in shape. However, when you match, so as you imagine a regular absorption band of any material, in the moment in which the band depth changes, also the shoulder will change. So by matching the band depth and seeing that the shoulder or the width of the band does not change, this is a clear evidence that the shape is not varying.
So like previous, you said that there is another minimum centered at 2.95. Is it true or not?
It's true, yeah.
So there are two minimum. One is centered at around 2.85. The other one is centered at around 2.95, right?
Correct.
Okay, great. Thank you.
Okay, I think that's the time we have for questions. Thanks very much. Okay.